Okay, let's start. Chapter 1, Introduction and Historical Perspective. For this chapter, we will first talk a little bit about semiconductor physics, and semiconductor devices. So this will be needed for your understanding of the later on chapters. So I know for the nanotechnology student, you have taken NE. I remember it is NE342. So this one is about a semiconductor. So you have learned those materials. So here I just give you very brief review of the basics. So for the semiconductor, we first think about silicon. So there are also other semiconductors. For example, 3, 5 group, 3 and 5 semiconductors. This includes gallium nitride. So gallium nitride is very popular. It is the most popular material for the light emitting diode. This gives the blue light emitting diode. So gallium arsenide is very important for the optical electronic devices. Indium phosphide is a popular substrate material for the 3-5 semiconductors. It is also possible to have the group 2 and 6 semiconducting materials. For example, zinc oxide is semiconductor. Zinc sulfide is also a semiconductor. CD, Fe, this is also semiconductor. Those CD, Fe, this is the important material for the quantum dot. We know if we go to the shops, there is the quantum dot TV. So this refers to the quantum dot material. The most popular material is the CD, Fe for the quantum dot display. So now let's look at the silicon a little bit more. The silicon is similar to the carbon. So carbon, we have the graphite and the diamond. Graphite structure and diamond structure. For silicon, it's mostly diamond structure. It is also possible to have the 2D. So for carbon, we have the diamond structure, and also we have the graphite. There is also monolayer. It's called the graphene. It is also possible to have the monolayer of silicon, which is called silicon. I think silicon, something like that. But this one is very difficult to synthesize. So now we look at the silicon single crystal structure. This is a diamond structure. The diamond structure is effectively, it is like a face. This is the face-centered cubic. But we have two sides of it. So we have two sides of the face-centered cubic with the offset by this amount. So this is the one set. This is offset. You can see this is like this item here and this one and this one. This is FCC. So we have two sides. The other one is offset. It's offset by the amount of this one, by the amount of this amount. So we have two FCC structure to form the diamond structure. So actually we can calculate. So what's the coordinate for this item? We can assume this one to be the coordinate here to be 0, 0, 0. This one we can say 0, 0, 0. So this one we know is along the diagonal direction. So this one we can say x, x, x. Now this is the coordinate for this one. So we know that the distance from here to here is the same as the distance from here to here. We say this is like item A, O. So we know OA equal to square root. So A, the coordinate for A is x equal to 0, y equal to A over 2, and z equal to A over 2. So the A is the distance from the here to here. So this is the at the center of this surface, at the center of this surface. So that's why it is 0, A over 2, A over 2. Then the distance from here to here, the distance of AO will be 0 minus x squared. X minus 0 squared plus x minus A over 2 squared plus x minus A over 2 squared. So it's given by, so x squared plus 2 times x minus A over 2 squared. So this is the distance from here to here. So distance from here to here is square root x squared. So this is 0, 0 equal to this one. So I will set them to be the same. If they are equal to each other, So we can find out that x equal to a over 4. So that means the second face-centered cubic is offset along the diagonal direction by a over 4. So this is the coordinate for this item. So now we want to know the number density of the silicon. For instance, here we want to know how many silicon atoms within this unit cell. So first we count about the corners. We have the corner. So corner we have totally 8 of them. 8 items at the corner. Each of them had 1 over 8 inside. We have 1 over 8 inside. So totally we have 1. Then we look at the surface. So we have how many on the surface? So we have totally 6 on the surface. Each of them had half inside and half outside. So the surface we have 3. So now we look at how many inside. So we know what? So this one offset to this one. So this is inside. So this one offset to this one. So this is also inside. And this one offset by the same offset come to this one and inside. And this one offset to this one is also inside. So we have totally 4 inside. So we have totally 4 items inside. Then we have totally 8 items inside the unit cell divided by the volume. We give this number. This is the number density of the silicon. So this is very important number because later on when we talk about doping concentration, so we refer to this number. So you should remember this number. So we know that the silicon is a semiconducting material. So actually, without doping, the conductivity is quite low, because at the room temperature, some of the electrons, so each silicon has 4 nearby atoms. So you can see here. So each silicon has 4 nearest neighbors. So here we have each silicon has 4 nearest neighbors. At the finite temperature, some electrons will be excited to become free electrons. Then leave behind a mobile hole. This will contribute to the conductivity. But because the thermal energy, which is equal to kT, so K equal to the thermal energy, K, this is the number. This is the thermal energy, kT, divided by electron beam. So this one, so kT, K times 300 Kelvin divided by the charge give you 0.026. So the thermal energy is only 0.026 electron volt. The energy band gap for the case of silicon is 1.12 electron volt. As a result, very few electrons will be excited. The number is called this is called intrinsic undoped silicon. So this is the number given by Ni. So this is Ni as a function of the temperature. So at the room temperature is given by 1.45 10 to the power 10 per cubic centimeter. You can see this is 10 to the power 10. And this number is 10 to the power 22. So you can see so very few electrons are excited. So generally, the intrinsic carrier concentration is given by this formula here. So T is the temperature. This number here, this number here is roughly half of this energy gap. This number is roughly half of this energy gap. So this is the drawing is here. So this for the silicon. For the case of the germanium, so germanium has smaller band gap, so get higher Ni. For the gallium arsenide and the gallium phosphide, those are the 3,5 semiconductors. You get smaller Ni because they have bigger band gap. So we know that silicon has very low conductivity when undoped. To increase the conductivity, this can be done by the doping. So normally we use the group 3 and the group 5 items as the doping. For instance, when we replace some silicon with the group 5 arsenide here, this will have 5 electrons. So 4 will be used to form the electron pairs, and then it contributes to 1 free electrons. So we can also use group 3 boron. The boron has 3 electrons, so we miss 1. Then we have this one mobile host, This is the p-type doping, n-type doping. So boron is almost the only p-type doping for the silicon. For the n-type doping, so phosphorus, arsenate, antimony, they're all very popular. But for the p-type, it's almost always a boron. So when the silicon is doped, so we have four different charges. So we know we have electron and hole. They are mobile. They will contribute to the current flow, and we leave behind ions. So we have this positive ion and negative ions. So those are the ionized donor and ionized acceptor. So they will not flow. They will not move. They will not contribute to the current flow, but they will affect electrical field. So they will affect the flow of the electron and holes. So now we can also look at the doping from the point of view of the energy band. So here is the conduction band, and the valence band. So this is the dopant energy level. ED is the dopant donor energy level. EA is the acceptor energy level. At very low temperature, approach 0 degree, so we have electrons. They are freeze out. They stay at the donor level, and this one is empty. This one is filled. So when we increase the temperature, electrons will be excited to the conduction band, and here electron here is also excited to this acceptor level. At the room temperature, all the electrons is excited, and here all the energy level is filled, so leave behind the holes in the valence band. So the reason that they're all excited because the number of the energy state is much higher in this conduction band than the number of the energy state at the donor level. The same is true for the acceptor level. So this is how the doping works. So at the room temperature, they're all excited. There are almost no left behind. So we can also see this in another diagram. So you can see at the low temperature, the free electron concentration. Now here we talk about n-type doping with arsenate. At low temperature, the free electron concentration is 0. It corresponds to here. So we have low temperature, not excited. So there are no free electrons. So then it go up at the room temperature. At the room temperature, they are all excited. This is called the extrinsic region. This is where the device operation temperature, because the number of the carriers can be decided by the doping. But at a very high temperature, the Ni become important. The intrinsic carrier concentration become important, because from here we can see at high temperature the Ni go up. So the Ni go up. They go like this, go up. So at a very high temperature, this temperature here, a few many hundred Kelvin, the Ni will be higher than Nd. Then we say the silicon become intrinsic again. So this is the temperature for the process. For example, we do the oxidation process. The temperature will be like more than 1,000 Kelvin. Then it become intrinsic. So intrinsic means the doping become unimportant. Here is the definition of the doping levels. For the moderate doping, we have 10 to the power 16. So this 10 to the power 16, this gives the silicon about 1 ohm centimeter resistivity. 1 ohm centimeter resistivity. You can see this number here is much higher, much lower than the silicon number density. That is 5 to the power 22, but much higher than the intrinsic carrier concentration. This moderate doping, this less doping, a very less doping, heavy doping, a very heavy doping. So even for the very heavy doping, 10 to the power 20, it is still only about 1% of the silicon atoms. So now we look at the electron and hole concentration. So when we have the both doping, we have both n-type and p-type dopant. So we know that from here, so we have 4 different charges. So the overall there should be neutral. It should be neutral. So this charge plus this charge will be the same as this charge plus this charge. So you can see it here. So the Nd plus P. So ND plus P equal to NA, the positive charge equal to negative charge. This is called the charge neutrality. So we have two unknowns. So we know ND and we know NA, but we do not know P and we do not know N. So we have two unknown numbers. So we need another equation. So we know that for the intrinsic semiconductor, the charge concentration is Ni, which equal to P and equal to N. So actually, then you have this NP equal to Ni squared. So we have this. This is the case for the intrinsic semiconductor. So actually, the same relation also holds for the extrinsic cases. That means, so when we have doping, this is also true. So we also have this equation. So now we have two equations, two unknown N and P. Then we can solve N and P to give you this formula for the doping. This formula for the electron and hole concentration. Now we look at different cases. The first case is N-type doping. For the N-type doping, the ND is higher than NA. And the difference, you can see the doping level, the number is something like this, the 10 to the power 5, even for the lightly doped, 10 to the power 14 or 10 to the power 16. So the doping level is much higher than Ni. Ni is only 10 to the power 10. So this term can be ignored compared to those terms. Because that's why, so we can ignore this term, ignore Ni squared. Then this one come out, so N equals to ND minus NA. Then P is given by Ni squared divided by N, so equal to Ni squared divided by ND minus NA. So this for the N-type. For the P-type, so we have the same formula here, so we can still ignore this term, and we have P equal to Na minus Nd and N equal to this formula. So now let's look at what will happen. So when we have the electrical field. So when we have the electrical field, electron and holes, there will be a drift velocity. So without electrical field, this is the thermal random thermal movement. This is called random thermal motion. With the electrical field, electron will move opposite to the direction of the electrical field. This is called drift. It's called drift velocity. So for the rough approximation, we see that the drift velocity is proportional to the electrical field. This number here, the proportional number, is called carrier mobility. So what is the unit? For the carrier mobility? So mu equal to V divided by E. We know the speed is equal to centimeter per second. This is the speed. Electrical field is volt per centimeter. So this gives you the unit of centimeter square volt second. So this is the unit for the mobility. So when we know the mobility, so we can calculate the current density. The current density is given by this formula here. So now how to derive this? So we assume that we have a box. So we have a box with the free charges. So we have a box here. So we have many charge. So the charge is moved at speed of the v. So the distance from here to here is given by v times delta t. So the surface area, here the area is S. This side area is S. So we know that the current is given by Q divided by T. So Q. So we see how many charge will pass through this interface, this area S within a time limit of delta t. So all the charge here, V times delta t times S. This is the charge. So equal to Q times V delta t times S times the carrier concentration. So this is the carrier. So the carrier concentration times the volume times the Q. This gives you the charge. Then the current is given by so here we have delta T here. We have delta T. So then the I is given by Q divided by delta T, so equal to Q N V S Q N V S. Then the current density. This is the current density is I current divided by the area, so equal to N Q V. So the current density. So you have to bring S to the left side. You have N Q V. So this is the current density. For the case of electron, so when the Q is negative charge, so we have minus Q N V N, and this is the velocity for electron. So we know that V is given by mobility times the electrical field. So you have this one. So this is the electron current density. The same way we can have the whole current density is given by QP mu P E. This is the whole current density. The total current is the sum of the electron current and the whole current is proportional to E, proportional to the electrical field. This is the conductivity. Conductivity given by 1 over resistivity equal to Qn mu n plus Qp mu p. So now we look at, now we want to derive J equal to sigma E. We want to derive this one, J equal to sigma E. So we assume we have a block. We have a block, so we have the charge. So we have the current moving inside the block, this current. So we know the Ohm's law, V equal to IR. V equal to IR. So V, if the distance from here to here is L, so V equal to E times L. V equal to the field times the length from here to here is L. So here the side wall is S. So I equal to, so we say I here. R equal to, we know that rho L over S. This is the resistance. The resistance for this block is given by resistivity times length divided by S. So the L here will cancel out. L here will cancel out. So I over S. This is the J. So we leave the rho again. So equal to, we have this formula here. So E equal to J times resistivity. Then J equal to sigma E. So sigma equal to 1 over resistivity. So now I see that. So we have this formula here. So that means, so when we know the dopant concentration, we can figure out what is the conductivity of the semiconductor materials. For the case of the low doping concentration and small field, the mobility for electron is 1500. And that's for the hole is 500, the mobility. But this for the small field and the small doping concentration. So we have, when it is very heavily doped, the mobility will be smaller because of the scattering by the dopant atoms. And from here, we also see that the electron mobility is higher than the hole mobility. So NMOS is faster than PMOS. So now we want to get some idea about the speed. So here we have the thermal motion. The thermal motion is roughly given by something like this. The speed of the thermal motion is given by, so 1 over 2 electrons equal to Kp, right? Boltzmann constant. This is the thermal movement. So we know room temperature Boltzmann constant. This one equal to 9.1 10 to the power minus 31 kilogram. Then we can find out the speed of the random thermal motion. The speed is 10 to the power 7 per second, centimeter per second. So this is the speed of the thermal motion. For the drift, it's given by mu times E. So if we have like 1 volt, this is the typical electrical field, 1 volt per micrometer. Then mu, we can take 1,000. We can take mu as the 1,000. Then we also get the drift speed is also 10 to the power 7 centimeter per second. So you can see for the typical typical situation, the drift velocity is the same order as the thermal motion of the electron and holes. So now we want to give an example of how to calculate the resistivity or conductivity when we know about the doping of the semiconductor. So now we assume we have a silicon sample doped with 10 to the power 16 per cubic centimeter of boron. So we want to know what is the resistivity. For the case of this doping, we have mobility equal to 450. So this a little bit slower, a little bit lower than this value because of the dopant scattering. So this is the mobility. We know that Na is 10 to the power 16, 10 to the power 16. So Nd equal to 0. So then P equal to this number. So N is very, very small. So how to get the N number here? So N equal Ni squared over P, right? Ni equals 1.45 10 to the power 10 squared divided by P 10 to the power 16. So this number you can see, we can ignore this like a 1. So 10 to 20 divided 16, we have 10 to the power 4. Then resistivity given by this formula here. Resistivity 1 over Qn mu n plus Qp mu p. So the resistivity. So you have 1 over Qn mu n plus Qp mu p. So the n is very, very small. This one can be ignored. So we have this left behind. And then we put the number in, the electron charge, carrier concentration, mobility, we get 1.4 ohm centimeter. So now we consider the same silicon sample with this doping. We dope additionally with 10 to the power 17 per cubic centimeter arsenic. This is the n-type doping. Now we want to know the resistivity. For this doping concentration, the mobility for electron is 600, but this is lower than this 1500, but this one is 600. So we have lower mobility because we have higher doping concentration. So when we have a lot of dopant, the charge will be scattered by the dopant atoms. As a result, the mobility will become lower. So anyway, here we have Na 10 to the power 16, the same as here. So Nd 10 to the power 17 is the number as here. So N is Nd minus Na is 9 times 10 to the power 16. So P you can calculate the same way. P equals to Ni squared divided by N. Ni squared divided by N. So you can see N is this number, but P is very, very small. So then we have the same formula here. In this case, so we can ignore this term. We have this one. Then we put a number in. We get 0.12 ohm per centimeter. The sample converted to the n-type material by this additional doping. Okay, thank you.